thank you all for coming. I will continue my course on maximally hypoelliptic differential operators and sub-Riemannian geometry. So I will recall the last theorem that I wrote from last course, first course. So there is this theorem by Helfer and Noriga, and just so that from 79, which says that let G be a graded, simply connected nilpotent Lie group and D a differential operator homogeneous right invariant. It doesn't matter, right or left invariant. Differential operator on G. Then, so if I have this, the following are equivalent. 1, D is hypoelliptic, and 2 for every. So this is a space of irreducible unitary representations, and I remove the trivial representation. Equivalence classes of irreducible unitary representation. So this is unitary representations. For every such representation, pi of D, d pi of D, I think, is injective on C infinity of y, smooth vectors. So we had this theorem from last course, and now this theorem, we want to use this theorem as a local model from which we deduce hypoellipticity for differential operators on smooth manifolds. Okay, so now let M be a smooth manifold. And again, it's without boundary, and I will fix some vector fields satisfying Hormander's condition. Hormander's condition. Of depth n. Of depth n means that I use at most, at every point, I use at most n commutators. Okay? And so if I have this, we said, so the first observation we had is that for all D, for any differential operator, D can be written as a polynomial in the vector fields. And P is non-commutative polynomial. And here, with coefficients in C infinity of M, and we defined the Hormander order of D as minimum of degree of this polynomial. Of course, the polynomial is not at all unique, and so we define the Hormander order to be the minimum degree of this polynomial. Okay, so for example, if I have x1 is d over dx and x2 is d over dy, then the x d over dy, then the Hormander order of d over dy is 2. Because I can write it as a commutator, and I cannot write it as a linear span. Now we want to use this theorem, so we have to create a group, simply connected graded Lie group. We don't really have, I mean, the simplest thing is to just take the biggest group possible, and then try, if it's possible, find a smaller model. Okay, and so we take the following. So let, so the, okay. Should I move this? So let G be the free nilpotent Lie algebra of depth n with generators So what this means is the following. So what this means is that G1, so G1 is the free vector space generated by these elements. G2 would be the free vector space generated by commutators. So R, so direct sum I less than G, R of xi and xg. And I is less than G because I have the Jacobi identity and the identity of a Lie algebra. And then G3 would be generated by higher Lie brackets and so on. And Gn would have n Lie brackets, and I force the Lie brackets to vanish after n. So
what's the difference with the x tilde and x?
So x are vector fields on the manifold. Yes. X tilde are just variables, like formal variables. Okay, but I think of them as the vector fields. I want to think of them as the vector fields.
But there's no connection between the bracket of x tilde I, x tilde j, and the bracket of xi and xj.
No, no.
Mm-hmm.
So so all of this is till now is very formal. Okay, and so these are just. So here I once said this in one of my talks. So Poincaré has this citation that mathematics is the art of giving the same name to different objects. And so the idea here is the same thing. I want to give the same name to this. Anyway, so I have a linear obvious map. So here's a connection. So I have a linear map from the Lie algebra to the algebra of vector fields. So this is the Lie algebra of vector fields. Which sends xi tilde to xi, and then commutators to commutators, etc. Now there is so it looks like it's a Lie algebra homomorphism, but it's not, because so this map is not in general the reason is that in the Lie algebra itself, I forced all of the Lie brackets to vanish after n, while on the manifold, that's not necessarily the case. So for example, if I had these two Lie algebras, two vector fields, d over dx, and x2 is cosine of x, or sine, doesn't matter, d over dy, then I need one commutator to generate. So in this case, my Lie algebra would be generated by 3 elements. This element, and then the third one. And the Lie bracket and the map would send this to d over dx, this to cosine of x d over dy, and this to the Lie bracket, which is the derivative of cosine, which I know what it is. So I think there's a sign. Yes. I learned this so many years ago. So anyway, so now higher Lie brackets between d over dx and this thing wouldn't vanish on the manifold, but they would vanish on the Lie algebra by construction. Okay? And so this map is not in general Lie algebra homomorphism, which will play an important role in a moment. Okay? I want to erase, not erase, so I want to erase. I will erase this part. We'll keep this. So now the idea is extremely simple. I start with my differential operator, which is a polynomial in the vector fields. The local model of D at a point x would be, so I will just try dx would be, so I want a differential, I want to apply this theorem by Helfer and Noriga. So I want a differential operator which lives on my group, which is homogeneous. So I take my polynomial, I remove all of the lower order terms, and I replace coefficients, I freeze coefficients, so each coefficient I replace it with its value at the point. And now I take this. Now this is a right invariant differential operator on my group G. So this is right invariant differential operator on G. G is the Lie group which integrates this Lie algebra. Okay? And so I want to apply Helfer and Noriga's theorem to this operator, so I take its value d pi of this operator. So now I define the principal symbol of D at a point x and at a representation pi. Pi is a representation of the group. This is a point in the manifold to be d pi of this thing, dx, which I could also write because d pi is a group homomorphism. So this would be p max x of d pi x1 tilde d pi xk tilde. Now, let's say a naive theorem would be something like this. So theorem would be something like this. If this thing is simply connected. Yes. So G is a Lie group. It's not Z, it's S. It's a simply connected Lie group which integrates this Lie algebra. And so a naive, let's say, not naive, but the first step would be if this thing is injective for all representations except the trivial representation, then D is hypoelliptic. For every x in M. Now, the reason why I say this is, so this is true. This theorem is true. The reason why I say it's naive is that this condition is very strong. So even for elliptic operators, this is very strong. And we'll see the problem in a moment. So. Till now, I didn't use which?
The xi have some bracket properties. I mean, it's not a free. The xi don't form a free algebra. Not without the tilde.
Yes.
So where does the specific of xi appear in this?
So in this theorem, no.
It doesn't appear.
No. So. This theorem is extremely naive. Let's put it this way. I will do it for elliptic operators. I will explain what's happening for elliptic operators, and then essentially, your problem is that, or at least the problem you are discussing is that here I put for all representations. So essentially, I didn't care about all of the Lie brackets that the vector fields have. I just took all possible representations. And so it's like, okay, it doesn't matter what the Lie brackets do. So this is extremely strong. There is two problems with this theorem. The first problem is that this thing is not well defined in general for any representation. By well defined, I mean the following. Here, to define it, the first step was to write my differential operator as a polynomial in the vector fields. And then I computed it in terms of the polynomial. And so I could ask, okay, if my differential operator is written as two different polynomials, and I do the same thing, do I get the same result? And the answer is no. And the reason is extremely simple, and it also explains why this theorem is strong. So suppose it's already elliptic. So suppose there is no need for commutators. So if n is equal to 1, I don't need any commutators. So in this case, my Lie algebra, there's no commutator, so it's just a free vector space on my vector fields. And I have a linear, and Horman's condition is just saying that these vector fields linearly span the tangent space at every point, but they don't freely linearly span. They don't form a basis, they form a generators. So I have this map from this to the tangent space, from this to vector fields. And I have this map which is this map so it's evaluation at a point x. Now this thing is surjective. That's Horman's condition. Okay. Now if I take its dual, then I get a map from Tx star m to G star. Okay. Now, my group is commutative, so irreducible unitary representations are just G star. And so you realize immediately that this thing can only be well defined for these xi which are in the image of this. Because then that's a principal symbol. So if xi is in Tx star m, and I compute this as a representation which is the image of this. So I compute it here, then this would be the classical principal symbol. So I realized two things. The first thing is that it's not really well defined for all representations. It's only for those which come from the tangent space at the point x. So that's where commutators or relations, it's not just relations between the commutators, but also linear relations between the vector fields enter the picture. The second thing is that I don't really need injectivity, which here would just say that it's non-zero for all representations. I just need it for some representations, which are those which come from the image. So now the goal is to find, in the general case, where I have a group and non-trivial commutators, the set of representations which represent the cotangent or the tangent space, if you like, here. So So I will take it as a black box for the moment, use it to write all of the theorems we need, and then I will go back to define this set of representations. So there is some set, so as a black box, there is, for every x in M, there is some set of representations, which we call the Helfer-Noriga cone. At x. And now this set of representations, which I will describe but once I write the main theorem. So the first thing it satisfies is that this thing is well defined. So theorem, this is joint work with Junkin and Reladakis and Junkin. So theorem, this is well defined for all x in M and for all phi in this set of representations. The second theorem is that we can, in this theorem, instead of having to suppose injectivity for all representations, which was here just silly, I would have to just check injectivity for the representations in this set. So now I can improve this theorem. I can actually improve in both sides, the hypothesis and the conclusion. So we'd have this theorem now. So the hypotheses are M is a smooth manifold, x1, xk vector fields, satisfying Hormander's condition of depth n, and D, a differential operator of Hormander order n. The following are equivalent. So the first thing would be that for all x in M and for all pi in this set, except for the trivial representation, this is injective. And the second, so now it's an equivalence with a much weaker hypothesis, or much more natural hypothesis. And the second is that for every S in R, I defined the Sobolev spaces last week, I think. I don't remember. The Sobolev space.
I don't think you mentioned Sobolev
Yes. And for every distribution, du is in H. I'll rewrite the formula. I want to keep this. So recall. So if S is in natural numbers, then the Sobolev spaces are defined with this formula. This is the inhomogeneous Sobolev spaces. The classical Sobolev spaces are defined using the exact same formula, but we replace the Hofmann order with the classical order. Okay.
What's this Tx or tau x?
This? It's the Helfer-Noriga cone, which is a black box, which I'll describe.
It's a black box.
For the moment, it's a black box.
Okay.
It's what represents the tangent space. It's tangent, the cotangent space. It's in the elliptic case, it would be the image of this. So it's really the cotangent space. This thing is injective because that's surjective. So it would be really the cotangent space in the elliptic case, but in this setting with commutators, it will also take into account commutators. It's really, I will explain it in a moment. Okay. So the important things here is that first, so here we weaken the hypothesis. I don't need to check injectivity for all representations, only for representations in this set. And the conclusion is much stronger. I get the best possible regularity I can ask for, which is the exact same thing I have for elliptic operators. So now I can say, where is this one? So if n is equal to 1, then this thing is just elliptic regularity C. So this is elliptic regularity C. In this case, this set, tau x is just the image of the cotangent space. This representation is the classical principal symbol. And so being injective would just mean that it's non-zero. And the Sobolev spaces would be the classical Sobolev spaces. So now this was conjectured by Helfer and Noriga in 79. They proved in 85 in a book 2 implies 1. So they gave a formula for this set, which will be, I will give their formula, but I also give other formulas for this set. So But anyway, they defined it, and they proved that 2 implies 1. They conjectured the equivalence. They proved 1 implies 2 in 2 important settings. So the first is when big N is equal to 2. So just a step slightly more complicated than this. And also the other situation where the vector fields have a constant rank, but also their commutators have constant rank, and their iterated commutators have constant rank. So all the way till all commutators, everything has constant rank. So in this case, they also proved this theorem. The reason why the constant rank is easier is because in this case, you can essentially, instead of having here a very big group, which has much higher dimensions than the manifold, you can use a much smaller group. And then this set becomes just representations of this much smaller group. And so the statement...
The group may depend on X.
It's a group may depend on X, but that doesn't pose a big problem. The problem happens when this set is not the set of representations of a group, which happens precisely when...
Can you describe it in terms of coadjoint orbits?
Yes, so that's what we'll do. So the idea is extremely simple. So I want to look at the time. So in the elliptic case, this set came from... So I will define the dual of the set. Let's put it this way. This set corresponds to a cotangent space. I will think in terms of tangent space. So I looked at the image of this. So instead, I will just look at the kernels of this. Okay? And so this is what we'll do to define this to X. So for every X in M, I will look at the kernel of this map. So this is a linear subspace of G, which has codimension, which is equal to the dimension of the manifold. And I think, and I really want to think of G over the kernel. Of course, that will give me a linear isomorphism with Txm. And so I really want to think of this quotient as a tangent space at a point X. Okay? Now, the first thing you notice that this thing is not a Lie subalgebra. This is because this map is not a Lie algebra homomorphism. And now we make we found out. I don't really have a good way of motivating why this works, but it's how it works. You look at these things. So this is a dilation on the Lie algebra. The Lie algebra is graded, so it has its own dilation, which we have used in last week to define homogeneous for differential operators. And so I look at these things. This is a linear map. So these are, again, linear subspaces, and again have the same codimension. And now, I use my favorite fact in mathematics, the fact that Grassmannian manifolds are compact. And so these things, as a sequence, as t goes to 0, always have a limit. And so we define this space. So G X 0. The 0 is because this is an 8-hour course, and so this will become a group weight later on. So Gx0 will be all of the subspaces H inside G, which have the same codimension as the dimension of the manifold, such that I can find the sequence xn which goes to x, tn which goes to 0, such that alpha 1 over tn of kernel of the natural of xn goes to H. Yes. In other words, what I'm doing is that, so another way, if you like this more, is that I take this map, so I put an inclusion of this inside Grassmannian of the Lie algebra cross M cross R plus star and I took the closure of the image. So the image. This is obviously an embedding.
Cross R plus.
In R, yes, in R plus. Otherwise it's.
So this big GX, I mean the G is for Grassmannian, not for Booth.
Yeah, so the G is for Grassmannian. And usually I would use Maximal on tech, but I have no idea how to distinguish between all of these on the blackboard. So I would use different notation on LaTeX, but if you can do them, please go ahead. Anyway, so yeah. So the important things here to mention. So the important. So the first thing which is obvious is that the kernel looks at linear relations between the vector fields. This is the kernel, so this is from the free nilpotent Lie algebra to the tangent space. So the kernel just looks at linear relations between the vector fields and their commutators and their iterated commutators. So it's the space of all relations. And so I just took dilations of this and took limits as Tn goes to 0 and xn goes to x. So basically, I'm looking at all of the possible relations which happen between the vector fields and their commutators. So the first thing to say is that H, for all H here, H is a Lie subalgebra. So each one of these things is not a Lie subalgebra, but at the limit, they become Lie subalgebras. Basically, what happens is that when you take this dilation, the error term, so this thing was a Lie group homomorphism, except when you go higher than n commutators. And so when you take these dilations, more or less you are putting a zero factor, or an error term factor in this failure to be a Lie algebra homomorphism. So when you take the limit, it really becomes a Lie algebra homomorphism. Okay? It's easy to prove, but can be tricky if you don't know how it works. Okay. Anyway, this is a fact. This is true. It's always a Lie algebra. It's always a Lie subalgebra. And now I really wanted to think of G over the kernel as the tangent space. But that's not really a good identification. What I really want to think, so the tangent space, the Sub-Riemannian tangent space, the Sub-Riemannian. Tangent space at x in M R. So here this would be the homogeneous space of the Lie group quotient, the Lie subgroup which integrates H. Okay.
And there are plenty of H's.
Yes. And so this is the second point. If these things have constant rank, so all of these have constant rank, So this is called the equiregular condition. Then this is the condition under which Helfer and Origa proved their theorem. So in this case, H is unique. So this Gx0 is just one subspace. And so in this case, so there is only one tangent space. So there is only one tangent space.
But when you write the Sub-Riemannian tangent space is or are G mod H, this is a definition or?
This is a definition. I will justify it in the time that remains. These spaces exist. I call them the Sub-Riemannian tangent, and I will try to sell this.
But you have many of them.
Yes.
So you put on this space.
Tangent spaces.
I mean, it's more fun when you have more spaces. Yeah, I don't need this. So now I can describe this set 2x in two different ways, at least two different ways for the moment. So the first way is the following. So 2x is as follows. So if I have a representation, so if I start with a representation, so let pi be a representation here, an irreducible representation of my group. Then pi is in 2x if and only if. So what happens is that I look at this representation so my group acts on this homogeneous space G over H by left translation. And so it gives me a unitary representation of G on this Hilbert space, L2 space. And now this representation is not irreducible. You could think of it as just Txm over L2 of Txm. That's not at all irreducible. So usually not irreducible. And now the condition is that P has to be weakly contained in one of these representations. So they exist in H such that phi is weakly contained in these representations. Weakly contained, I recall what it means. So pi is weakly contained here. This means, that's one definition, is that for every f in Cc of G, continuous function, complex valued continuous function, if I define the operator pi of f, this operator, f of x, pi of x, dx, so dx with respect to a Haar measure, and I define this operator to be the same integral Gi. So this is an integral over the group. Then norm pi of f has to be less than or equal to norm pi h of f. So that's one equivalent formulation of weakly contained. Is not necessarily the most intuitive, but okay. We know from classical theory or representation theory that this thing decomposes into reducible unitary representations. Weakly contained means it's one of these factors which appears in this decomposition. Okay. So essentially, tau x is all of the representations which can come from the tangent space. Okay. Now, that's one way, maybe not very intuitive or maybe not very useful for doing computations, but it's very useful for proving theorems. Like this is the key. Yes.
In the equilibrium case, the subgroup that you have H is it's normal energy.
Yes.
Okay, so you have group structure.
Yes. Here, yeah, I didn't mention this. Here, this group would be normal. This subgroup would be normal, and so G over H would be a group. Okay. You can say more, which I'll say no. So this would be the description that I would use if I want to prove. This is the description that we use to prove this theorem. Now, other descriptions which are actually useful to do computations would be so. Okay. So the orbit method tells us that the representations of any simply connected nilpotent Lie group, in particular this group, is homomorphic. That's also topological space. It's in bijection with natural bijection with the quotient of the Lie algebra by the coadjoint action. So coadjoint action. Coadjoint action. By coadjoint action. So I could also ask which elements here can appear in G hat. And so another description. So let xi be in G star. Xi is in tau x, if and only if xi is in the union of H in this set H orthogonal. The reason why we look at H orthogonal is extremely simple. H were limits of the kernel. Remember, I looked at the kernel of these things. The limits of kernels, dilations of these things. But before I do dilations, I was looking at this. If I take the orthogonal, then this would be, by linear algebra, this is the same thing, canonically isomorphic to the image of the tangent space. And so when I take the orthogonal, I'm essentially looking at the same thing as the image of the tangent space. And so this would replace what I had in the elliptic case, which is the image. Okay.
Yes, this is true for every.
This is linear algebra.
Every subgroup, the two just inside.
What?
H orthogonal is exactly the set of representations.
So this is not true. No. So this is fun. So I will explain.
Because
yes. Yes. Anyway, the reason why we take H orthogonal in connection with what we did in the elliptic case is this identity.
But is it clearly G stable?
This? So this I will explain. So I will also explain the equality between these two things. So one important fact about Gx0, which I kept hidden till now, is that for every G in G and H in Gx0, GH, G inverse, sometimes I write the subgroup, sometimes I write the Lie algebra. So this is also in Gx0. So this set is closed under conjugation. So now I can prove, for example, the equivalence between this point of view 1 and 2. Why? So orbit method, so the orbit method says that xi, if I take an element xi in G star, and I look at the irreducible unitary representation associated to this, then pi xi, this would be the irreducible unitary representation associated to xi using the orbit method, using this bijection. This thing is weakly contained in this, if and only if xi happens to be in the union. I write disjoint union, but it's not really disjoint union. Here it's also not disjoint union. So it's union of H in H, the coadjoint action of G, no. Orthogonal. Then take the closure. So it's union of all of the coadjoint action. Oh. So I take my Lie algebra and take all of the conjugates, and then take all of the orthogonals, and then take the closure. And so this set defined here is now the union of all of this over all H. So the first definition, would be the union over all the elements H in Gx0, the union over all G in G of the closure of the head of G. I could also flip it this way. So, or yeah. Now, ignore the closure for the moment. If I didn't have this closure, this is fine till now. So if I didn't have this closure, then this, because of this property, this union is just a redundant union, because I'm taking union over all H and also union over all G, but the adjoint is already here. So if I didn't have the closure, then this thing would be union in H in Gx0 H orthogonal. This is without the closure. But it's already closed. So it's also true with the closure. And the other way is obvious. But, so this is already closed. So you get equality. Because this is already closed. It's closed. Of course it's closed because I have the closure. It's defined as the closure of something. So from here we get the equality between these 2 points of view. Now I will, this time I remember, so I'll take a pause of 5 minutes, and then I will give a third point of view, and then I will explain more or less how we prove this theorem using pseudo differential operators. Okay, so someone asked what is the orbit method, so I will recall it very, very, very quickly. So if I have xi, an element of the Lie algebra, then we consider the bilinear form from G cross G to R which is xy tends to xi of the Lie bracket. This is antisymmetric because of the Lie bracket. And so it's antisymmetric, but not necessarily non-degenerate. So it has a kernel. And so it's a codimension of the kernel. From linear algebra, the codimension of the kernel of this is even, because on the complement it would be a non-degenerate antisymmetric form. And so the theorem, so the first theorem in the orbit method is that you can find a Lie subalgebra. So there exists some Lie subalgebra, such that it's Lagrangian for this form. So h and h vanishes. And the second is that it's maximal with this property. So the dimension of it, its codimension is half the codimension of the kernel of beta x. This always exists. And because of this property, I could define, so if H is the subgroup which integrates this Lie algebra, then I have a representation pi which lives on the group, I have a character, one-dimensional representation, which is pi of the exponential is the exponential of xi of h. So now this would be a group homomorphism because it vanishes on the commutators. This condition just means that xi vanishes on the commutators. So I could define a unitary representation of the subgroup, and then I can take induced representation. So I take induced representation of this, and I get a representation G on some Hilbert space H, which is L2 functions, which are so this would be so unitary operators on H. H would be functions from G to C, which has the property that f of gh is equal to f of g pi of h. So pi of h for all g in g and h in h. And you further require them to be L2. So that means that when I take the absolute value, so now in absolute value they will descend to equivariant. So this would be a function on g over h. And so I ask that the absolute value is in L2 of g over h. And g acts on this Hilbert space by left translation. And so the orbit method tells you that all irreducible unitary representations appear this way. So it tells you that this thing is irreducible. All of them appear this way. And if you start with xi, then there is that choice which we made to create the representation, which is h. The class of this representation doesn't depend on h. So all of them. So this finishes so all of the theorems here. Okay. So what I wanted to say now is to try to justify why I called this G over H, these homogeneous spaces, tangent spaces in Sub-Riemannian geometry. So recall, so if X is a metric space, so here we follow ideas by Gromov to define tangent space in Sub-Riemannian, tangent space for metric spaces. So recall a few things. So if X is a metric space, and I have two sets, in X, then the Hausdorff dimension, the dh of A and B would be the supremum of the distance between, no, no, it's not like this. It's maximum it's a min-maxing, so it's maximum, max-min. This is min, and this is max. And then it's max again. So it's max, min, max, max, min. Now where is it? So supremum of d of A, y is in B. This is called the Hausdorff distance between subsets, A and B. And now we have this brilliant definition. The Gromov-Hausdorff distance between two metric spaces, x1, x and y and d. So this is a distance between two subsets. The distance is not very intuitive, but if I have A and B, it's something like this. Okay. This is on time. So now, a definition due to Gromov is that if I have two metric spaces and I want to compute the distance between the metric spaces, then I define this to be the infimum of the distance between I of x and I of y, where I is an isometry inside any metric space. This is the isometry. Huh?
X disjuncture y.
Yes. Okay. Isometry on something which is partially defined, some metric which is partially defined. You could also, you don't read any points, you could just say it's the infimum over all possible distances you can define as a disjoint union. You take x union y, you know a distance on x, and you know a distance on y, but you don't know what is the distance between x and y. So you take all possible metrics on x union y, which would also force it to satisfy the triangle inequality, so you have some constraints. And then among all these distances, you compute the Hausdorff distance between x and y.
The distances on the union have to be compatible with
With the distances. The whole union has to be a metric space. There is always a distance which make it work. You just take anything which doesn't satisfy the triangle inequality, and then take infimum over all possible passes which would make it work. So you can always make it work. Maybe with infinite, that has, if x is compact and y is compact, that's fine. Anyway. Now we say that Xn, a sequence of metric spaces, converge to a metric space if the distance Gromov-Hausdorff of Xn and Xnd is equal to 0. It goes to 0. So it's a way to define limits of metric spaces. And if now this definition doesn't really work very well if the metric spaces are not compact. And so to rectify this, if I have a sequence xn, dn, and some sequence of points, then I say that this converges now in the pointed Gromov. So this is in Gromov-Hausdorff sense. So this is in the pointed Gromov-Hausdorff distance if for every r the closed ball of inside xn with this center of radius r. So this is now a metric space, which you would expect it to be compact because that's a closed ball. Of course, this is not true in general, but in the what?
Bounded metric is okay.
Bounded metric. So you will only apply these things to metrics for which the unit closed balls are compact. So this thing.
No, you don't need. Just bounded metric is okay.
What do you mean bound?
The diameter is finite.
Okay. This has to converge in the Gromov-Hausdorff, now in this sense, to this x and r closed B. Yeah. And now the example, the typical example would be if you take z and you take the usual distance and you divide by n. Let's say take the origin. So I look at z. When I divide by n, that means that instead of the distance between 2 points being 1, it's 1 over n. So now my points are getting closer to each other. And so the limit as a metric space of this thing would be what you would expect, which is r with the usual distance and the origin again. And another example would be, or interesting example would be, if I start with a manifold and I take a distance. So what happens here is that I divide by n. When I divide by n, it's as if I am looking at z from far away. Now I can do the opposite, which is I look at the manifold, but from very close. So I divide by t, because that would be the same variable which will play a role. And I take a point x. D here is the Riemannian distance. Fix some Riemannian distance. And I take the limit as t goes to 0. So this is the opposite of what I'm doing here. I'm really zooming in at a point x. And so this metric space would become the tangent space at the point with now the constant Riemannian distance and the origin. So the space when you look at, yes? With the space when you look at it from very close, it becomes just linear space. Yes?
And do we get the Hausdorff topology with the Gromov-Hausdorff distance? Like, do we have a unique limit, for example? Why is it like Q, for example, instead of R?
I think you have a unique limit here under hypothesis on your metric spaces being compact and length spaces or something like this. Here I don't know, I'm not sure. Yeah. Is it clear so far? So now I can state the connection with the previous theorems. So if I have, now there is a theorem by Chu in the 30s, which says that, so now we go back to Sub-Riemannian geometry. So we have a manifold with some vector field satisfying Horman's condition. So the theorem says that for every 2 points x and y in M, I can find an absolutely continuous path, absolutely continuous path between them, x, such that its derivative almost everywhere is in the linear span of the vector fields. If the vector fields satisfy Horman's condition, this is always possible. And so we can define the norm, the length of this path, to be the integral from 0 to 1, the norm of this derivative. Now, how do I define the norm? You can just take a Riemannian metric on the manifold. Beleish has a better, there's in fact a canonical Riemannian metric here, which comes from the fact that I chose my vector field satisfying Horman's condition. But here I could just take any Riemannian metric, and it would work. dt. Okay. There is a canonical Riemannian metric up to choosing. So I can say it very quickly. I had this surjective map from the Lie algebra to Txm at every point x in M. This is surjective by Horman's condition. So if I fix any Euclidean metric on this G, I can project it by this linear map and get a Riemannian metric on Txm, which would depend smoothly on x, because this depends smoothly on x. So if I want a Riemannian metric on my manifold, I could just start with a Euclidean metric on the Lie algebra. And there is. And here it only matters on G1. And on G1 there is an obvious one, which is you make all of your vector fields x1 tilde, x2 tilde, etc. On orthonormal basis. So that's the one Beleish uses. But for the theorem that I will write, you could also use any Riemannian metric.
Is there a condition which dualizes the distance just by saying that the distance of x and y
of the functions?
F of x minus f of y for f such that xi of f,
Yes, probably. You take supremum over f of x minus f of y, and you bound the gradient in the
only in this direction.
Only on the directions of x1 till xn, which would be more intuitive. Anyway, you can define now the sub-Riemannian distance between x and y to be the infimum of the length of this process. And now, motivated by this, you can say, well, if I have a limit, then that limit would also be the tangent space. So now I can state our theorem. If I have a sequence xn which goes to x and tn which goes to 0 plus, and it happens that these things if I have these conditions, so this is one of the, so I took one of the groups, which I called, so I took one of these groups, but I also took how it was created. It was created as a limit coming from xn and tn, okay? And then the theorem says that if I have this, then the limit as n goes to infinity in the pointed Gromov-Hausdorff distance of the manifold with the sub-Riemannian distance divided by tn xn, this goes to the important things here. So first, on the limit. So this is the origin. This is just the identity coset. The homogeneous space G over H has its natural family of vector fields satisfying Horman's condition, coming from the fact that my group acts by left translation, and so I can just take the push forward of the vector fields on the group, which already satisfy Horman's condition, and then look at them on G over H, and so they will also satisfy Horman's condition on G over H, and so it also comes with its own Sub-Riemannian distance. So this is the model space that I have. The point here is that I divide by Tn as Tn goes to 0. That's the same as before. But the point is that I changed my origin point. It happens that in Sub-Riemannian geometry, in Riemannian geometry here, I could have taken any sequence xn, which goes to x, and I took any sequence Tn, which goes to 0, and this limit would remain 2. And so this convergence was uniform. That's literally the definition of being uniform. And but it happens here that this is not uniform, at least if this family of groups were more than one group. If it was one group, then that just says that the limit is uniform. If it was more, then that just tells you that the limit is not uniform, and there happens to be many of them depending on the origin. Okay, and this is, so before I forgot, when xn is a constant sequence, just you start at the origin and it's just constant, then it doesn't matter what Tn are, this thing will converge as t goes to 0, not just as Tn. It doesn't matter what subsequence you take, it will converge as t goes to 0 to something here. And in this case, this computation was already known. This is a theorem due to Bilaish from 91 or 90. Okay. Now, I will just say that this theorem is very natural in the sense that if I take these two vector fields, dx and x dy on R2, so these satisfy Horman's condition. And so this is a typical example of two vector fields which satisfy Horman's condition, and they are not equiregular. They don't have the constant rank condition. And so I have a problem at x equal to 0, which is this line. It's either this one or this one. 50% of chance of getting. Anyway, so it's this one. And away from this line, these two vector fields already linearly span the tangent space. So this distance is just a Riemannian distance. And you get a problem when you approach this line, where it really has a different behavior. And so the idea is that now, if I take my xn, if I started with the xn here, which is what Bilaish does, which is xn a constant, then I always have the Sub-Riemannian structure. Because any small ball around this, I'm taking limit in the Sub-Riemannian distance, pointing Gromov-Hausdorff distance sense. So I'm looking at unit balls around this. So here, I will always have the Sub-Riemannian structure because I will always have this line in my limit. But if my sequence of points is, say, here, and I'll also I look at the balls around these points. But if I choose the xn to converge slow enough to 0 and Tn to converge fast enough, it's the relative speed between xn and Tn. But if I choose it good enough so that actually I will always just avoid this line, then I should never expect the limit to be a Sub-Riemannian space, which is what Bilaish obtains. I should always expect it to be a Riemannian space. Okay, so this explains that there should be at least 2 tangent spaces, one which Pelage already computes and one which is Riemannian. And it's not far-fetched to expect that actually there is a whole continuum of them which connects depending on how the speed, what is the speed between xn and tn. Okay? Now, of course,
the Riemannian structure in the limit could be degenerate.
no, it will not. I mean, I'll do computation in a moment. Show it. It turns out it's actually extremely easy. So now the obvious question which one has to answer is, okay, so I know, or I expect it to be that the relative speed between xn and tn is what determines what the limit looks like. I want to actually have a formula for this. What is the relative speed? And so what this theorem tells you is that this relative speed is just this limit in the Gromov-Hausdorff dense. So it's just a linear algebra problem. The whole thing just reduces to a linear algebra problem, which is computing this limit in the Grassmannian space. And so I will do a computation with this example, where the speed will appear. So in this example, the Lie algebra, I'm taking the free Lie algebra, so it has 3 components. I added x. I shouldn't add. I mean, yeah. I could have used x1 tilde, x2 tilde, and the Lie bracket, but use this one. I could have named them differently. So that's a Lie algebra. And so the linear map is, of course, the obvious map, which sends this to dx, this to x dy. I'll use x, y, and z. So the linear map sends x to dx, y to x dy, and z to dy. And so the kernel of this map at point x would be the one-dimensional vector space, which is generated by the vectors y minus xz. Linear span of this vector. And now remember that I do dilations. This is the only relation between my vector fields. So I do dilations on them. And so y has order 1, because it's one of the vector fields that I took, while z is a commutator. So I multiply y by 1 over t, while z I multiply it by 1 over t squared. And since I'm taking linear span of this, I could renormalize by multiplying by t. And so this would become r y minus x over tz. And now I have the speed that I'm looking for in the Grassmannian. So if xn, so now I take a sequence xn which goes to 0. I'm computing everything at the origin. So I take xn, so if I have xn and yn, so if xn and yn goes to 0 and 0, and tn goes to 0, and xn over tn goes to lambda in R, then this thing converges to R times this vector y minus lambda z. And you are missing the one which comes from infinity, projective space. And so if xn over tn goes to infinity, you flip, and so you get rz. So h here in this case would be rz. And h here in this case would be this one. Now, you see the difference between the tangent space that Pelage obtains and the tangent spaces we obtain. So the one that Pelage obtains would be xn and yn constant sequence. So xn is 0, so lambda is 0. And so this would be just y, the subspace given by y. And so the quotient would have x and z would play a Sub-Riemannian, will factor into the Sub-Riemannian part. Okay? But in the case of xn over tn, which goes to infinity, which is the opposite, my h is equal to rz, so I kill all of the higher order things, and so my quotient has only x and y, and so now it's a Riemannian space, which is just x. Now the quotient is just the tangent space in the usual Riemannian sense. So you more or less, this tells you that if this limit is infinite, then this limit in the Gromov-Hausdorff distance is slow enough to evade all of the subtleties of the Sub-Riemannian metric. Okay. So this at least justifies why I call this the Sub-Riemannian tangent spaces. Now I'll explain a sketch what we need to prove this theorem that I wrote from before on this Helfer-Noriga conjecture. Yes and no, kind of. So that's an interesting remark. So Helfer and Noriga had the idea of taking sequences xn, which goes to x, and tn goes to 0, and taking limits, but they took limits in the cotangent space. They never used Grassmannian topology. Okay, so their definition of tau x was this union over h in gx0. That's not exactly how they defined it. Okay, there is a slightly better way to define it by slightly simpler way to define it by avoiding the Grassmannian topology, but that's their original definition. But they come from analysis, and from the point of view from how they approach the problem, it's actually very natural looking at xn and tn, which goes xn, which goes to x, tn goes to 0. Now, Beleish, who comes from geometry, he never considered changing the base point. And it's very unnatural to, I mean, I think it's natural, but it's very unintuitive to expect the result to be different, because it's the same in Riemannian geometry, it's the same in equi-irregular case, and so you wouldn't expect the result to be different. Or he didn't expect it, I don't know. But from the geometry part, no. It's only people from analysis who consider this, but not with the Grassmannian. I mean, the main key, I think one of the key insights from our work into this Helfer-Noriga conjecture is that we rewrite the set that Helfer and Noriga wrote using limits in the cotangent space as this union. And then this union, we rewrite it in a much more complicated way as the union of the closure or the union of the adjoint. And then we see this as the representations which are weakly contained in. This is much more useful because it connects your representation with the tangent space in the manifold. You can actually use this to prove inequalities. I can describe the original definition. That shouldn't take long. So the last point of view, so xi, so this is Helfer and Noriga. Xi is in tau x, let xi. let xi be an element in the coadjoint in the dual of the Lie algebra, then xi is in x if and only if I can find a sequence xn which goes to x, tn which goes to 0. Now, in my case in the union, and I said, and I can find a subspace H such that xi vanishes on H. Now, in their case, they would say, and you can find some cotangent vectors on the cotangent vectors on the manifold, so that when you take, so you had these maps. Remember, you had these maps from the Lie algebra to Txm, which we keep using all the time. And so what they ask, and so if you dualize these maps, you get a map from Tx star m to the Lie algebra. So what they ask for is that these maps with the dilations. So you first compose with the dilations. I think you have to Tn. Yeah, so you take star of this, and then you apply this at xin. So xin lives in the cotangent space of M, and when you apply this at xn, you can make it live on G star. And so you do this, and now you ask that this converges to xi. This is in much simpler language. This tells you that if you take xin and you multiply with Tn, and you take, so xin, so you have your vector fields which satisfy Harmadas condition. So you take xi at xn. So xin, you can apply them to these vector fields, and you multiply with Tn. You ask that this converges to xi applied to the corresponding vector field, the corresponding element in the free nilpotent Lie algebra. And you ask that the same thing happens to commutators. So xin with the commutators xi and xj at xn. So now this is interesting because the commutator, you of course cannot compute it with this knowledge alone. And then you have to remember that it's a commutator, so you multiply with Tn square, and you ask that this converges to xi of the Lie matrix, etc. So that's how they obtained their set.
But it's exactly equivalent to what you said.
It's exactly equivalent to what I said. That's because of complexity of the Grassmannian. So it's the exact same thing. They just never tried, to my knowledge, they didn't really try to, instead of taking limits with the index being xi, and take limits of the kernels in themselves. Yes. Anyway, so that was the original definition. So how do we prove the theorem? So we So the first step, so remember the theorem had this statement. One, this principal symbol is injective. The second, this is for all pi, x and m, for all pi into x, except the trivial representation. The trivial representation corresponds to xi is equal to 0. Which is always there because once you take the orthogonal. Yeah. So you have this. And the second is that for every S and R, even though I didn't really define sublove spaces for R, only for N, and for every U in C minus infinity of M, du is in H tilde S locally implies that U is in H tilde S plus N of M locally. Here N is the Hofmann order of my differential operator. Now I wrote the theorem with these two conditions. Now I need a third one, which I didn't mention, which is that if M is compact, then this is also equivalent to D. So M is compact, so my Sobolev spaces now are actual Hilbert spaces. So this operator, bounded operator, is left invertible modulo compact operators. In the case of elliptic operators, this would say that it's Fredholm. But here, because here I asked the operator to be injective, which is lift type invertibility. So here I asked that it's also left invertible modulo compact operators. If I replace injective with surjective, then here I would get right invertible modulo compact operators. And so if I wanted to be Fredholm, I would ask this to be bijective, from smooth vectors to smooth vectors. Okay. Now, this turns out to be the key statement to prove this part. And so the first step, reduce to case M is compact. When you prove the elliptic regularity theorem, it makes absolutely no difference whether the manifold is compact or not. You don't care, you never use it, and it never enters into the proof. It just happens that when the manifold is compact, what you did at the end just tells you that your operator is Fredholm. But you never really use this fact. Here it turns out that to prove this theorem, we have to crucially use the fact that M is compact. So the first thing is that I can always reduce to the case of M is compact. In fact, I can always reduce to the case M is a sphere. For the obvious reason, so if M is compact, then I have 3, so that's nothing. If M is not compact, then I'm proving 1 is equivalent to 2. Both of these statements are local. So I could just suppose that my manifold is an open subset of Rn. And then I put this open subset inside a sphere. And then my vector fields, I put them inside the whole sphere using, say a cutoff function. So now they obviously don't satisfy Hofmann's condition. I add to them vector fields which, on the complementary part, which will satisfy Hofmann's condition. And then I add to my differential operator another differential operator which acts on the complementary part. And so I reduce to the case where M is a sphere. So I can always suppose that M is compact. Okay? So now the goal is to so now I want to prove that M is compact. I want to prove this equivalent to this equivalent to this. And just a remark. If you replace D with D star D, we can reduce to D with D star. You can also, if you want, reduce to the case where D is self-adjoint. Okay. Or you could just say that we will prove the theorem in the two-sided version, which is that D is bijective. This is true with the adjoint having also the same property. And here D is Fredholm. That would be that. So the two-sided version of this theorem would be here is bijective. Here, not only D has this property, but D star also has this property. And here this would be that D is Fredholm. Modulo, so it's the same as being invertible modulo compact operators. Okay, So the way we'll prove this theorem is almost the same way as one proves the elliptic regularity theorem, which is by constructing a pseudo-differential calculus. So I will write the properties we need, and the properties we actually succeed at proving with this calculus. So, so for every k, every s, so I used k for the number of vector fields. I will use it for the order of my operators, because I really like k as the order from my operators. We can define pseudo-differential operators of complex order, but to prove this theorem we don't need them. So for every k and r we define some.
Sorry, is it supposed to be obvious that if you prove it for self-adjoint, then you have the case of non-self-adjoint?
You take d star d. If you can prove it for the two-sided version, and then you take.
No, I understand you take d star d, and then it's obvious that if sigma is injective.
Then sigma d star d is also injective. It's so sigma. Yeah. So this I didn't mention. I was going to mention it here. Okay, it is true. Which follow. Okay, I can write this statement this way. If this is injective and sigma of d star is also injective, that would also imply bijectivity.
Okay.
I mean, let's put this for the moment. So I'll prove this. So for every k in R, I have a subset of endomorphisms of C infinity of M. So I have some subspace of endomorphisms of C infinity of M, which are also continuous for the topologies that I defined, if you really care about this, which satisfies the following. So the first thing is that it's an algebra. So psi k of M composed with psi L of M is inside of psi k plus L of M, and it's closed under a joint. Psi k of M star is equal to psi k of M. If I used here complex numbers, then I would have added k bar here. But other than this, it's fine. So the second property, I won't use this at the end. So the second property, if D is a differential operator on M, which has Hofmann order K, then D is an element of psi k of M. The third important property is that if P is in psi 0 of M, so if it's so here I'm supposing M is compact, as I said. Here I use the condition M is compact. Here I didn't need it. Here I use it. So if it's a pseudo-differential operator of order M, then P extends to a bounded operator from L2 of M to L2 of M. If P is a pseudo-differential operator of order negative, then P is a compact operator. In addition, P is compact. So not only is it bounded, it's also compact. Okay? There is an inclusion which I don't use, but it's also true if you want. Here, psi k is inside the psi k plus 1. They are included inside each other as long as the difference is an integer. So how's this? Okay. So now these are algebraic and analytic properties. What I also need is that the principal symbol does extend to these operators. So for every x and m, and of course I have the same issue as before, the differential operators, the principal symbol is only well defined for pi into x. So here I also have a principal symbol which is only well defined for the representations into x, except the trivial representation. I have this is an operator which satisfies a few things. First, it's compatible with this. So if P was a differential operator, it's again the principal symbol we defined from before. Not the classical principal symbol, the one we just defined. And it's algebraic in the sense that the principal symbol of P, Q, X, pi is the principal symbol of P, X, pi, the principal symbol of Q, X, pi, and the principal symbol of P, X, pi star is equal to the principal symbol of P. I'll just mention one small thing. Because I really don't like having even more mistakes in my talks. This thing is in the, so this is not the adjoint in the sense of unbounded operators, as in you take the complement of the graph, and this equality is that when you take the adjoint on smooth vectors, you would get equality. Because the adjoint using unbounded theory of unbounded operators on Hilbert space, the domain might be bigger. So the equality here is when you restrict to the domain. Or you can just even make an inclusion. Now, all of these properties, if I removed Hormander order and replaced it with classical order, I removed the principal symbol, this symbol, and replaced it with a classical principal symbol. That's just the same thing for classical pseudo-differential operators. Now, here is the one where things start to get different. So in the classical, so for elliptic, so this is so I will write the condition in the elliptic case, and then I will explain how it differs. In the elliptic case, what happens is that for every k in R, for every p, if this principal symbol doesn't vanish, then you can find an operator such that QP minus the identity and PQ minus the identity is regularized. Regularizing means that it extends to the space of all distributions, and it maps all distributions to C infinity vectors. Okay. So this is in the elliptic case. A very close by property. So this is, let's say, 5 prime. This is invertibility. The other one is vanishing. So if the principal symbol of P vanishes for every xi non-zero, then the operator was actually of order 1 less. This is in the classical case. This is also elliptic case. Now, both of these properties, I cannot say that they are false, but I'm more or less I'm convinced that they are not really true in the case that we prove. Okay? What I can say is false is the following thing. So the first thing which happens, which poses problems, is that if D has Horn under order K, and its principal symbol vanishes for all representation, for X in M, and for all representations in this set, that does not imply that D has Horn under order K minus 1. With the classical principal symbol, this is true. With Horn under order, this is false. So this already poses problem if you want to apply this, for example. If you want to extend this to pseudo-differential operators. Maybe D is not, has Horn under order, doesn't have Horn under order K minus 1, but maybe it's pseudo-differential of K minus 1. I strongly doubt it. But anyway, it makes it complicated to even have this. Okay? And so we will change them with two statements which look three statements which look weaker, but so the first one is that, so here I could find a parametrics, an actual parametrics. I will replace it with the statement that I can find a parametrics up to the symbol, in the sense that for every k in R, for every p pseudo-differential, if this thing, so I will write it in the version, so if this thing is injective for all pi into X with the 1 removed, X and M, then I can find another pseudo-differential operator of order minus k. So here I had the condition injective, so I cannot expect two-sided, I just expect one side. And so what I expect is that the principal symbol of QP minus the identity, this one vanishes. Yes?
And you cannot even say that it has order like k minus epsilon?
For differential operators, no, because that makes no sense.
Yes.
For pseudo-differential operators, I don't know if this is true.
Not even
They are not related. Different trees.
Okay, so first they are not related, so you cannot say they are pseudo-differential operators of order k minus epsilon. You could ask whether they extend to Sobolev spaces of order k minus epsilon. I don't know if this is true. Okay, unfortunately I have to erase things. So I need this, and then I will replace it with another one. I added two dashes because that's this one I will keep it. So the new one, which is okay. So in general, I have a parametrics, but for some operators, I know that I have a parametrics. So for all k in R, I can find one operator, at least one, such that there exists Q in psi minus K of M, such that QPK minus the identity is regularizing. Actually, I can suppose that it happens both sides. So here, I said that for every operator which happens to be injective, I can find an operator which at least makes the symbol vanishes. And here I say that, okay, I also have for every order one operator which has an actual parametrics. This is more or less power of form under sum of squares.
Sorry, this is more or less?
Power, so this is pk is equal to sum of squares power k over 2, more or less. So I know by previous work of many people, before we started working on this conjecture, that this thing holds. Because people knew how to prove form under sum of squares theorem, and they also knew how to construct powers of it, even in the non-equiregular case. So this thing we knew is true. So this is, and then remains the last one. I will write it. So I defined, so if P goes from, if P is in a psi k, then it defines a bounded operator from HS to HS plus k to HS of n. I was going to define these Sobolev spaces, but for time reasons, and since I really want to write all of the conditions today, I'll just suppose that I did define them. And so this is the version which is I wrote with pseudo operators of order 0, but here is with general order. Here is of n. This is clear? Okay. So now, if in the classical case, what happens is that if my operator has a symbol which vanishes, then it becomes an operator of order k minus 1. So if the symbol vanishes, then this map, and instead of going to S, it goes to S plus 1. Now the inclusion of S plus 1 inside S is compact. So you deduce that this is compact. And so what we will prove is that if the principal symbol vanishes, I don't know if it maps to S plus 1, but at least I know that it's compact. So if P and its principal symbol, actually I need it for just 0. Here I just need it for 0. So here in L2 of M to L2 of M, if the principal symbol vanishes for all representations, then this thing is compact. So I don't know if my operator has negative order, but it behaves as if it was one of order, as the question was asked, maybe of order minus epsilon, for some epsilon small enough. So I don't even know if it maps L2 to H epsilon for some positive epsilon. It's in some sense H0 plus. It's just slightly better than being order 0. Okay. So I will end here, but I had 5 minutes pause, so I am on time. I forgot this. So using all of these axioms, what I just wrote, one can give a very quick proof of our main theorem, which I will give next time in 2-3 lines. It's very, very quick. And then I will explain how one constructs this calculus, which has all of these properties. So, thank you.
Other questions? I have a question.
Yes.
You didn't say anything about the commutator of two pseudo-differential operators?
It's in general not. In general, not even the principal symbol vanishes. So already you would have the problem, even if the principal symbol vanishes, you would have the problem that not necessarily this implies that the operator has order 1 less, But even the principal symbol doesn't vanish because the principal symbol takes into account the vector fields and their commutators. So if you take already two vector fields which have two of your vector fields, which you use in Horman's condition, take their commutators, that's also an operator of order 2. So it's simple, doesn't vanish. It's designed, it's by design because the group is not commutative.
And I have another question. You stated your main theorem for differential operators, but at the end, is it also true for...
Yes, it's also true for things here, whatever these things are.